Danny said, I'm Chris. I'm a research scientist with NVIDIA. So what I'm here to talk to you about is connecting task and motion planning to the real world. Particularly, the question is, so we would all like to have our robot that can do stuff around the house. Like, can I ask my robot to go get me a mug from the kitchen right now? And what is stopping us from doing that? So the question that I would like to pose to you, to everyone listening or watching, is, so to get one of these task and motion planning algorithms to work, what kinds of information do we need, and what kinds of state do we need to estimate to be able to make decisions? So let's see, is my slide going to advance? There we go. So first of all, task and motion planning, right? So what we want to do is be able to solve these multi-step tasks with hybrid state. So the methods that we have are usually model-based, usually, but not always, have a fully observable state space so that they use to be able to make decisions. So this allows us to do a lot of really exciting things. So there's some really complicated problems that people have been able to solve, like all the great stuff Wei Wei was just showing us. And there's through manufacturing tasks, 3D printing kind of stuff, tool use, scenes with many, like dozens of different objects, all kinds of interesting stuff that we can do with these algorithms. But the problem is that but there's still a lot of stuff that these things have issue with. First of all, like, we need to have robust perception to be able to act in the real world. We have to be able to deal with things like partial observability. We have to be able to find, dealing with stuff like if we don't know where all the objects are, we don't fully understand the effects of our actions, dealing with unknown objects in particular. So to be able to do it, so we need to be able to figure out solutions that work for all of these things. So how do we connect these perception systems so that we can be sort of robust to these kinds of issues with our task and motion planning algorithms? So there are sort of three possible strategies, three ways that you could kind of think about doing this. First of all, we could just have an explicit state estimation pipeline. What this does, so we have like object detectors that we've trained. So these are deep neural networks that predict object poses, gripper pose. They tell us exactly where the handle is. You get a 6-off pose for everything. We track all the poses over time, and we build some giant system out of all these different modules that will work together and give us the exact state for a particular set of modules, for a particular set of objects that we care about, right? Second of all, we can try to weaken that assumption a little bit, where we have something where we train some visual recognition aimed at specific predicates and control policies, so that we can capture sort of the hierarchical structure of the task, like knowing things like whether or not can we grasp this object? Do we have something in our hand? Is the gripper around the handle right now? Where should I go from here? Like, or what is the policy that I follow? So that's option 2. And finally, we could just try to avoid this entirely, go totally model-free, avoid all of our assumptions about objects, and try to build capabilities similar to what we have from task and motion planning algorithms, just from sensor data and from learning. And so going from point clouds to grasp poses, segmenting out unknown objects from their environment, predicting what's occluding what and what we need to grab first, and so on, all without any models at all. Right? So the first approach, let's go through what we've done. This is sort of our existing pipeline. This is sort of what everyone starts with, right? We have the explicit state estimation. So our explicit state estimation pipeline starts with just 60 object pose estimation. So our 60 object pose estimation pipeline starts with pose-CNN, which is work from RSS a couple of years ago, and that segments out the objects, predicts the centers of predicts object centers, estimates the orientation. That connects to DeepIM, which iteratively refines object pose estimates using models. So we can get very accurate poses initialized from pose-CNN. And then from there, we have pose-RBBF, RSS work from last year, actually. And what that does is that tracks objects over time, keeps track of a 60 distribution, and runs a particle filter, does global localization and tracking. We can also initialize that from pose-CNN. So we have this pipeline which will give us very accurate poses over time for known objects, right? And then from there, we integrate all this information together into something called DART, or dense articulated real-time tracking. What that does is that takes us, and we'll see the video feed here at the top, on the top left, is an image of what the camera is seeing, what the robot is doing in the real world. The bottom is our scene from DART. This is the different object models, like what the different things are in the scene, where the robot is. What this does is it integrates our data from different sensors, like our robot localization, our pose estimation. It tracks the joint configurations of the objects. So as this video starts, which it will now, there we go. We can see that, so right now the robot's not localized in the scene yet, but we do know sort of where where the arm is, and now it's activated some localization, and we can see it moving up to go grab the objects. This lets us track things like this tells us how open the drawers are indoors. It also lets us obey physical constraints, like whether or not making sure that objects aren't overlapping, and so on. And so this gives us a world model which is somewhat robust to occlusions, and it lets us really reactively track everything. And so let's see something that uses this in practice. So this is our RLDS system, robust logical dynamical systems, which is the idea of this is that what we're going to do is we are going to give the robot a particular goal, and it's going to construct a task plan with a bunch of different low-level policies that we know how to execute. And what happens is that and as it moves, it's going to reactively switch between these based on their pre and run conditions. So if it ever ends up outside of this state in a place where like its task plan is no longer valid, it can easily replan very quickly. But for the most part, it can just jump back and forth through this plan as I do things like nudge the object out of the way or close the drawer on it, and that'll let it quickly react to different circumstances, right? So this is robust to disturbances. It's nice, but it's still like very model based, right? And it doesn't really deal with partial observability all that well. So more recently, we have our system which was running task and motion planning in the kitchen. What the goal here, this system represents the object poses as particle distributions of where possible locations of where objects can be. So this is work by our intern Kaylin Garrett last summer. And what happens is that here we have the robot. We tell the robot to believe that the spam is in the bottom drawer. So the first thing it does is that it tries to open that drawer. When it wasn't there, it replanned, found a new possible location, sees the spam, and now it comes up with a plan that will actually take the spam out, put it on the counter, close the drawer in a second, and then go down and open the bottom drawer and put the spam away, right? So this system, this has got a lot more planning time than the previous system, but it can deal with partial observability. It can find objects, take the right actions to identify where objects might be, move stuff out of the way, open drawers, whatever, gather the information and make the right decisions. So this is great. Now the problem with all these systems, these systems still have one big fundamental underlying issue, which is that like all these, they rely very heavily on the pose estimates that we're getting. Errors in those pose estimates estimate or translate to very, very dramatic shifts in how well the execution works. So like if my symbolic state ends up being slightly different, or if objects are too close together and it thinks that something's not graspable, then we can easily end up stuck, and for no good reason, right? So also we have that whole elaborate pipeline that we were just talking about, right? We have like four different vision systems and four plus different vision systems, multiple sources of sensor data, everything getting integrated over time. So let's take a step back and try to rethink this. And this is sort of our implicit state estimation system. So the idea is that instead of estimating all these explicit low-level states for everything, right? There's all this information that we had about like 6-off poses of objects and of everything in the scene that we don't really need, right? What we really care about is knowing whether or not knowing the things that matter to the task plan are like the prerequisites to my actions, whether or not they're met, what kinds of policies, what kinds of actions I can take at different times, and sort of what those policies are that I'm going to follow. So let's take a short video clip, right? A few different frames of RGB information, sensor data. Estimate the logical state, the current set of predicates that are true, the things that I need to know to know whether or not I can execute my policies. We'll send that to a planner still, because let's say that we have a symbolic domain, but not anything to do with continuous information for that. If we have a valid plan, that's great. If we don't, we'll replan. If we have that valid plan, that's going to determine which action we should be executing right now. And then from that, we have a second neural network, which is going to take in our sensor data, give us some spatial information about what the world looks like, and estimate the position that the robot should go to, okay? Or the configurations of some low-level controller that's going to actually move there, right? Okay, so what does this sort of system look like in practice? So this here is a video of the output of all of the different sort of predicates that were predicted by the system. This is given by a simulated version of the real system that we collected a bunch of data on and then trained this model on. So what you see in this is that we have anything in black is it's correct, but old. It's been correct for a long time. If things change to correctly be estimated false, they'll be red, and true, they'll be green. And there's also a set of incorrect false positives and false negatives, which are important for a specific reason, so that I'll get to in a second. So what's going to happen here is that this robot is trying to put a sugar box, which is a white and red thing in the center of the image, away in the drawer. Same thing that we've been seeing. So it moves over, lines up, and you can see the predicates changing, and as it gets closer to the goal. And then it nearly lines up, and here, so I paused the video here, where you can see that it's got two things wrong, which is that it doesn't quite realize how close it is that it's graphed yet. This is actually kind of important because it's sort of a little bit conservative, which means that it'll sort of continue to execute a policy. Otherwise, it'll just keep oscillating. So once we do that, it quickly, like a frame later, it's gotten this thing correctly. It now knows it's updated its internal state. So now it knows that the arm is now next to an object. It's grabbed something. The arm and it believes that at least that the arm and the sugar box are connected. So now it'll presumably try to lift it up, which it does. But then we try to distract it by teleporting the sugar box away. And now its internal state is all in chaos, right? It doesn't quite know what's going on anymore. So the idea of the system, but it'll quickly react. The predicates correct themselves almost instantly. Its logical state's updated. It goes, moves over to the box, descends and picks it up. Right? It'll pick it up, and now it keeps reactively estimating what the state is. Every frame based on these predicates chooses the point. This is the same algorithm that's executing in the real world when I was like slamming the drawer and moving stuff around on the table on the robot, right? So it's able to use this sort of estimate this information accurately over time, and that allows it to robustly execute all these different things. And that means that we can give it different goals as long as it has the predicates to describe them, and it'll give it a new task, and it'll be able to get to that new state and execute well. So at the low level model, this whole model is trained to be able to learn a representation of the whole scene. So what happens is we get RGB information in, several time steps worth of RGB information. We predict the current depth and segmentation image so that as an auxiliary loss, it gives it enough structure so that it can actually understand what's going on in the scene, the relationship between the different objects. But that's the supervision that we provide it. And then there's so at the low level, what's happening is that once we've determined what action we need to be executing, that is going to be listed in the lower left-hand side of the screen, and then we can see what happened, what the current predicted goal is as things change in the world. And so this is going to be the same thing that we just saw, but at full speed instead of half speed. And so we can see that it sort of jumps. It thinks on the right side that the arm is jumping around. Those are jumping around because it's telling it, okay, try to get here, as it. Depending on what the current actions are determined based on that symbolic state that I was showing you on the last slide. And so again, we teleport it away. It's briefly confused. It adjusts, picks up the object, and can go and put it in a drawer, right? So cool. So the nice thing about this system is that it lets us, now we've got this thing which can learn a finite set of classifiers instead of doing the very hard problem of actually correctly estimating very accurate poses for everything in the scene. And then we can break it down in these subproblems, which are like, now I just need to learn a whole bunch of policies like this, which tell me where to go and how to make the changes that I want to make in the world. But there's one big shortcoming to this, right? Which is that it still required something. It still required me to give it basically a PDDL domain, right? To tell it like what my actions are, how they relate to each other, what their preconditions are, so that I can do this reactive execution. And that still takes a lot of, and we had to execute it in simulation to be able to get the data, right? And so now we should probably try to do a bit better than that. And so hopefully, like we won't necessarily have a perfect PDDL domain for everything that we have when we try to execute this in the real world. So what we want to do is remove even that assumption if possible, right? And in particular, we want to be able to deal with unknown objects. So let's start with just like basic capabilities for dealing with unknown objects for these kinds of plans. So we have so first of all, let's start to build this basic capability. We're going to start by trying to learn to grasp unknown objects. Okay, we have a simulation. We've got very nice simulations. So let's just put thousands of grippers in a scene, thousands of objects in a scene, and try to grasp them in thousands of different ways. This is work by Clemens Eppner. And so the idea is that, so now we've got this, we try this over and over again. So the robot will just try to grab all of them. It shakes itself to make sure that it's got a good grasp. And then we record the pose, right? So now we have a bunch of different data that gives us this distribution of all the different possible places we could grasp this object. And we can do this for all the different objects, right? Any object we can imagine. So then we move on to 6DOF GraphNet. So now we can take that data and we're going to try to train this, to train a model that'll be able to estimate the grasps. So given that input image, we get the point cloud. We train a model that'll sample a bunch of different graphs as a conditional variational autoencoder. We have a discriminative model, which will tell us which of those graphs are good. And that scores each of the different possible graphs. We use that information to refine our the grasp estimates. And then we can test it out in the real world. So we refine it, we get a good grasp. And so this worked 88% of the time. On first try, grabbing unknown objects. It's been trained now on almost 9,000 different objects from the ShapeNet, from 262 classes in the ShapeNet data set. So it's a very, very nice general purpose grasp model that can grasp in, and it's 6DOF, right? It can grasp from many different angles as is appropriate, which is important in a second, right? Because what we really want to do is grasp in cluttered scenes, right? We don't just want, not all of our objects aren't just going to be sitting out conveniently on the table for us. So in this case, we have this, so we have a scene with a bunch of different objects in it. There's one of these that I want to grab. Well, so let's segment all the objects out, tell us so we can identify which object is which, or at least know that they're different, right? We want to grab object 3, we want some mustard. So we take our 3D point cloud from this scene. We crop that point cloud out, and GraphNet, what I just showed you, is going to give you a whole bunch of different possible ways that I can grab it, but some of those are in collision. So let's train a model that'll be able to figure out which objects are in collision and which objects are blocking it, right? So this substantially improves the quality of the performance over just like naively just checking collisions with the point clouds in the scene. The first part, that instant segmentation, is trained in a similar way. So we have unknown objects. We can segment them out. We identify which objects are different, and now we run this model here, which is going to give us So what's going to happen here is that the robot's going to try to grab the mug in the center of the scene. So originally this object here is not reachable because we can estimate all of the different possible things, and we can see that there are objects that are possibly causing collisions here. And the one that's most likely to cause that collision is this red sugar box, the same one that our simulated robot was moving around earlier. It picks it up using GraphNet to estimate a good pose for it. We get it out of the way. And now we can go and pick up that mug. Now this is work by one of our interns, Aditya Murali, who was presented at ICRA recently. And so, yeah, so now that the object is free, we can grab that object and put it down wherever we were told to put the mug down. So this is like a good solid step towards like a fundamental task and motion planning capability without any of the models necessary for it, I think. But as we're working on developing these things, there are a few things that we're going to need to keep an eye on. First of all, we collect a lot of data. We make heavy use of simulation for testing and development. On the left, we have our real robot in Seattle. On the right, we have the video from the robot in our NVIDIA PhysX simulator. So models of the kitchen and the robot have to be physically accurate and photorealistic. So we have a bunch of different object property. We keep careful care to make sure that the masses and frictions and so on are good so we can learn some of these different rules. We have a lot of different physics tools. I'm sorry, is someone speaking?
Chris, 1 minute roundabout, just for your information.
Oh, I have. Okay, I might have started my timer late. Okay, that's good though. That works. Yeah, so we have Flex and PhysX, so we can simulate different types of objects, including deformable objects or particles. We have our simulation supports the Isaac SDK and ROS interfaces, so we can use a very similar version to the real system, including streaming sensor data and testing out our whole full perception stack and simulation and training there. The big bottlenecks for us are things like identifying the parameters of the simulation, so things like those frictions and masses and so on, and getting new assets, content, right? So we can actually simulate realistic environments. So just to summarize, so explicit state estimation leverages the accurate model-based object detection and tracking. The implicit version, we can just take the parts of it that we care about, like the logical predicates and high-level actions, and use them. But we use the model-based system to provide supervision. This still requires some knowledge of the domain. And finally, we work on the version without any state estimation at all, which does robust grasping and clutter from depth. And so thanks to all of my many collaborators, to Dieter and all the various interns and students at UW that we've worked with over the years.